blood flow to certain areas to help circulate the blood. And stem cells improve the conduction of intracellular electrical signals, so like to get signals to body parts to help move, and the reducing of cell death. And the reproduction of a cell from a stem cell, the results can result in newer, normal, and even younger cells. So there are two types of stem cells, two main types of stem cells, and they're neural and embryonic. This slide is on neural. And neural stem cells, they're self-renewing and they're multipotent, which means that they can only turn into a limited amount of cells. So like they can turn, if you want to change it into a blood cell, it can only turn into that cell. It can't turn into anything else. The abbreviation for it is NSC, and when you inject it into a site, it migrates and it replaces the dying neurons or any cell that is needed to replace. Embryonic stem cells, they're pluripotent, which means that they can turn into any more types of cells than a neural stem cell can. And you get them from the inner cell mass of an embryo. So it's basically a human fetus. And researchers have found that most people don't like using embryonic stem cells for therapy because they think that you're killing the human fetus when you're really not. So that's false. So some bone injuries, background bone injuries, they are, it's when the vertebrae of the body, it's squished. And there are two types of people that get bone injuries, and they're patients that have been in like a traumatic accident, so like a car accident, or they've been squished by, say, a bookcase fell on you. And the pressure that's placed onto the vertebrae, if it exceeds its stability, then the vertebrae will crush or crumble, and it will lead to back injury. And also patients with osteoporosis, and like I said before, it's when the bones become extremely porous, and it's easier to break them, and it's easier to injure them. And patients with osteoporosis, that's the most common bone injury. Some symptoms of osteoporosis is like major back pain. So like when you're walking or when you're sitting down for a long period of time and you get up, if you feel a sharp pain in your back, your spine will begin to curve because of the fact that the vertebrae is compressed. So normally the vertebrae is like rectangular, but when it's compressed, it pinches towards the inner part of the spine, and towards the outer part of the spine is normal, so it causes a curve. And it's called, when the spine curves, it's called kyphosis deformity. And you lose like a couple inches. When you get this disease because of the decreased size of the spinal column. So some treatments for bone injuries are like just prevention and period. Just don't get injured, because when you get injured, then you go through a process, and it's easier for you to get another injury. Exercise, once you are injured, exercise that and strengthen your back. Drink calcium. Medication, and there's a procedure where it restores the height of the bone. So basically, a doctor will inject cement into your spinal cord, and it injects it at the site of where the vertebrae was crushed, and it basically just makes it stronger and it keeps its shape. So this brings me to my research design. The purpose was to develop a therapy for vertebral compression bone fractures, and they hypothesized that the direct injection of AFCs to a vertebral bone would accelerate the bone regeneration. And the materials they used were adult male mice. They used the adipose cell stem cells. They used fibrin gel and bioluminescent imaging. The methods were they used porcine adipose stem cells, which are just like stem cells that come from the fat of a pig. And they isolated them and they labeled them. And the adipose stem cells were then transfected, which means they were they were mixed in with BPM, which I had stated earlier was bone morphogenic protein. And they created the bone defect, so they took a drill and they crushed the vertebrae of the mice. So the adipose stem cells, they were mixed in with the fibrin gel because it brings out its full potential, and it was injected into the part of the spine where the vertebrae was injured. And the cell regeneration, or like the process of the recovery, it was monitored in vivo, which is basically, it was monitored inside of the rat. So like they didn't take out the rats separately. They just looked at them. They were in an area where they could just monitor them every day. And then after 12 weeks, the mice were all gathered and they looked at the results. And the results were analyzed. Results: the cell death and there was cell death, like the cells that prevented the mice from moving and functioning their hind legs. There was replaced from the stem cells. And the first day when they first scanned the mice, when they first scanned them, when they first made the injury, there was a major bone defect. But after the 4th week, post-injury and injection of the stem cells, there was a considerable amount of recovery. And after the 12th week, there was a complete recovery. So that means after 12 weeks of the experiment, the mice were able to move again. And the adipose stem cells, they contributed to the new bones that formed because when it was injected directly at the site of the injury, it started to regenerate cells that helped reverse the defect. So in conclusion, adipose stem cells show the potential to repair bone defects and injuries in the future, and the results could lead to bigger and more advanced studies, like to reverse bone injuries. And this experiment could create a new approach to bone treatment and osteoporosis therapy. Thank you to Mr. Rhea, Ms. Alonzo, Dr. Miller, Dr. Williams, and Io for helping me with finding good articles and practicing. Thank you. Any questions, comments, or concerns?
You mentioned that the frequency of the greatest number of fractures we see are spinal fractures in the U.S. or
Yes.
is that correct? Is that mostly in people of a certain age, or is that just in general the most prevalent?
That's just in general. There's no specific age. It's just that's the amount of people that get spinal cord injuries a year.
Okay.
Ms. Alonzo?
Yes, thank you, Ms. Shannon. Could you explain some limitations of the study you presented?
Well, in the article, it didn't tell me how big the mice were, or how developed they were, or how old they were. So that could be a limitation because you don't know how effective it is on how big the animal was, or maybe the mice were small, so it worked better, rather than if the mouse was bigger, it wouldn't have worked as well. So that could have been a limitation.
And do you consider it a limitation, you said they use the stem cells from pigs?
Yeah.
Do you consider that to be a limitation and how it could translate to use in humans?
Well, yeah, actually, I don't really know. Ms. Rhea?
You mentioned that harvesting stem cells from a fetus does not kill the fetus. What else would you call that? Are you debating whether or not it's you could debate whether or not it's a human, but if I chop off my finger, I'm still killing my finger, right?
Yeah.
So if you're preventing the fetus from continuing to grow, you are, in effect, killing the
Well,
fetus.
no, it's not from the actual human fetus. That's what people think it's from. It's from the pocket. Like it's the fetus. It's from the embryonic stem cell it's taken from a 5-day-old fetus, so it's not fully developed yet, and it's taken from the sac that it's in. It's not taken from the actual fetus.
But if you're destroying that sac, are you not destroying the fetus as well?
No, because there are over 200 cells that make up the sac, and you're only taking out 10 10 or 20 years old. So it's not effective.
So not necessarily affecting the
No.
fetus? Okay, okay, that wasn't clear. Thank you.
Any more questions? Mr. Wright?
Regarding the treatment in humans, how far out are we in terms of finding this treatment as applicable to human testing? Or is this something that's very far in the future?
Well, right now, they haven't started